Before we can understand the physics of a figure skater's spin, we must first understand fundamental concepts of rotational motion. We'll begin by first understanding axis of rotation. Try picturing a pole entering from the top of your head and exiting to the bottom of your feet. You spinning in a circle would be your axis of rotation. Angular velocity is the rate at which an object is rotating about its axis of rotation. It's represented by the Greek letter omega and is equal to the change in angle over the change in time. To give a more visual example of what angular velocity would look like in motion, I'm going to show a change in angle over a change in time. So I'll be turning 180 degrees in about 1 second. Next, we have rotational inertia, which is the measure of how difficult it is to change angular velocity along the axis. It is dependent on the distribution of mass compared to the axis of rotation. It is important in showing us how changes in mass distribution affects changes in rotational motion. Its formula is represented by I and is equal to mass times the square of the radius. This is a free body diagram from a bird's eye view of a figure skater rotating in a spin. This center point is the center of rotation along its axis. This radius would be half of its wingspan, and then this delta angle is its change in position.
Before explaining angular acceleration, I think it would be best to explain non-uniform circular motion before. It is a change in velocity, and because angular velocity is changing, the system is non-uniform. That is why acceleration exists due to the measure of change in velocity. For the formula, it is alpha is equal to change in angular velocity over change in time. Whenever this is increasing, this is positive, and whenever it's decreasing, alpha is negative. For an ice skater, when they start spinning, the external torque is 0 because no outside forces are changing the motion. When no outside forces are acting on the figure skater, conservation of rotational momentum is present. Applying a force to the figure skater, such as pushing them over while spinning, would stop their angular motion. Since they're no longer rotating about their axis, there is no longer a conservation of angular momentum.
Now to demonstrate how changes in a figure skater's motion changes their speed, I'm going to use the formula for conservation of angular momentum. The equation is the initial inertia times the initial angular velocity is equal to final inertia multiplied by final angular velocity. So we're given this set of data. We have their mass is 50 kilograms, their initial radius is 0.7 meters, their initial angular velocity is 15 radians per second, and their final radius is 0.1 meters. So I wrote out the long version of this formula just by substituting the equation for inertia times the equation for angular velocity. So our mass is 50 kilograms multiplied by 0.7 squared multiplied by our initial angular velocity, which is 15 radians, is equal to our mass times our final radius, which is 0.1 squared, multiplied by our final angular velocity, which we do not have. So our initial inertia is equal to 24.5, and this is in kilograms per meter squared, multiplied by 15. And we want to isolate our final angular velocity to solve for it, so we're going to divide by the product of this, which is 0.5 kilograms per meter squared, and this is equal to the final angular velocity. So our final angular velocity is equal to 735. This is in radians per second. So to compare, our initial angular velocity was 15, and our final is now 735, which is a major increase. And this is due to the relation between inertia and radius. So decreasing radius, as we did here, from 0.7 to 0.1 drastically increases angular velocity.
From this previous equation done, we can see that for figure skaters, by using their arms, decreasing their radius, they're able to increase their rotational speed.
Now that we have covered the fundamentals of rotational motion as it applies to a figure skater, we are going to build on these concepts by learning the physics of composite rotational motion. In other words, we're going to discuss how it's possible for a figure skater to spin while supporting another figure skater as they revolve around them. This is called the death spiral. It's a move done by two figure skaters with the heavier skater, who we will refer to as person B, rotating in the center while essentially dragging the lighter skater, person A, in a circle around them by holding their arm. This is made possible by person B firmly placing the front tip of their ice skate in the ice, creating a pivot point or a center of rotation, which we will mark as capital P. By joining their hand with that of person A and applying a force, their two are now moving in tandem, therefore becoming a rigid body. Now that they have created a new composite system of rotational motion, their center of mass has relocated to the point of contact, represented by uppercase M, which is equal to the sum of person A's center of mass, MA, and person B's center of mass, MB. The radius of rotation, R, is the distance from the pivot point to the center of mass of the system. The distance between the center of the mass of the system and the center of mass of person A is represented by LA, and that of person B is LB. Before I can explain in more detail how their motion is possible and the equations associated with their movement, let's look at how the second law of motion applies to composite rotational motion. Newton's second law states that the sum of the forces acting on the system is the product of the mass of the system m and the acceleration of the system at the center of mass. This is a free body diagram from the top view of the death spiral, showing that the motion of the rigid body from the center of mass m. The center point is the pivot point, which is where person B has the tip of their skate planted. The distance between m and p is the radius r of the circle. The angular velocity, w or omega, is going with the motion of the center of mass. The centripetal acceleration we see is perpendicular to the direction of velocity because it points towards the center of rotation motion. This is the change in the system's velocity and is represented by the formula AC is equal to angular velocity squared times radius. The force applied by the ice on person B at the pivot point, F of P, is acting towards the center of the system. The formula for that force is F of P is equal to the mass of the system times centripetal acceleration, which is important to know because knowing the amount of force the ice is exerting on the person controlling the motion tells us how much force they are in turn exerting on the ice to maintain the rotational motion.
As we demonstrated the example of the death spiral and what its meaning is, we will now do a practice work problem example. So, as stated, how much force does the male skater have to exert on the ice to maintain his center of rotation, symbolized as P, and not drop his partner? So, with the practice problem example given, our male skater mass, symbolized as capital M, is 75 kilograms. The mass of our female skater, which is symbolized as lowercase m, equals 55 kilograms. The rate of rotation, symbolized as W, is 4 radians per second, and R is our radius when the male skater is pulling the female skater into a rotational circle. It is 0.55 meters. Ask yourselves, what formula are we going to use to solve this problem? Here I will show you the formula. So AC is our centripetal acceleration, the W is the rotational rate, and the R is our radius, which was all given in the practice problem, right? So this formula equals to this formula, which is the force of the person equals to the mass of the person times the centripetal force. And it could also be explained in this formula. So this formula equals that formula equals this formula, okay? So the force of the person equals the mass of the male plus the mass of the female times our rotational rate squared times our radius. We are going to use this formula as I explained, and this is what was given, which I also explained, and we're going to insert all this information into this formula, which is 75 plus 55, the masses of both figure skaters combined, times the radians per second, which is our rotational rate, times our radius. Okay, so 75 plus 55 times 4 squared equals 2080 times 0.55, and that equals to 1,144 newtons. So that will be the amount of force that our figure skater has to have in order to maintain the other figure skater.